Okay, this is a hypothesis test or paired t-test. It's scenario 2. Professor Andy McNeil measured the time in seconds required to, and this is page 141, required to catch a falling meter stick for 12 randomly selected students. There are 12 randomly selected students, dominant hand and non-dominant hand. So in other words, we're tested with the dominant hand first, and then we're tested with the non-dominant hand. So we have two separate readings. Professor Neal claims that the reaction time in an individual's dominant hand is less than the reaction time in their non-dominant hand. So we have dom is less than non-dom, right? That's probably going to be pretty helpful to us. So I have all the data, and I have two lists, and we have 12 individuals. So individual 1 for dominant hand was 0.177, non-dominant was 0.179. So for every single individual, we have two readings. This leads me to believe that since everyone was tested twice, we're working with a paired t-test. I need to enter the dominant hand in L1 and non-dominant in L2. And just to do that real quickly, stat, edit, and take a moment to go ahead and enter that data in. You may want to pause the video while you're doing that. Then it says test an appropriate hypothesis and state your conclusion. Well, if there was no difference, it would be equal to 0. All right, no difference would be equal to 0. But since he says that the dominant is less than the non-dominant, we're going to go with our alternative hypothesis saying mu d is less than 0. Now make sure that when we do our definition that we're going to go dom minus non-dom. And you always have to give what order you went in, all right? Because that's going to change your outcome. So let mu d equal the true population mean difference in reaction time, dominant minus non-dominant. Conditions, random sample. They gave it to us this time, so it's a random sample that's given. We have 12 participants, and 12 divided by 10, reasonable to assume that there are 120 students or more. The next thing is the difference in reaction times are independent. And basically that's the new one, and that's a new condition, but student 1's reaction time probably doesn't impact student 2, etc. So it's reasonable to assume that the reaction times are independent. All right. Lastly is normality. Well, they didn't tell us it was normal. We only have 12 pairs. I need 30 or more pairs. I don't have 30 or more pairs, so I can't say it's normal by central limit theorem. So I need to go ahead and graph this. Well, we already put the data into L1 and L2. To do this, though, I'm looking for the difference, which means I need to subtract them. So I'm going to go up the top of L3. I'm going to go second 1 minus second 2. And it did the subtraction for me. Now I'm going to get my box plot, second stat plot, enter, arrow to the left to make sure it's on, then drop down. And I'm going to arrow to the right until I get to the one with the outliers and press enter. My X list, all my data, that the paired data that I'm interested in is an L3, so second, followed by the number 3. And then I'm going to press zoom 9. Now, if it glitches like this, press clear, then press zoom 9. Okay, so this is the box plot that we get. I look at that and I go, gosh, I really don't know if it's that symmetric or not, but for College Board purposes, it is. We can use the trace feature, and we go, okay, that's negative 0.043, negative 0.0235, and you can just use the labels because this would be a pretty hard scale to draw. So that's what I did. Negative 0.03, negative 0.0235, etc., all the way across. And our statement is the box plot is reasonably symmetric with no outliers. The distribution appears to be approximately normal. Now I know we're claiming that's reasonably symmetric. There are no outliers, and it's basically saying it's symmetric enough. All right. The more symmetric it is, the better off we are, but we're going to say it's symmetric enough. Now, our formula is T equals X bar D minus mu D SD divided by the square root of N. Well, in this case, we know N is 12. We know mu D is assumed to be 0. So we need to get X bar D and we need to get SD. All right. So stat, calc, one variable statistics. My data list that I'm interested in is the differences. So that's L3. So second 3, enter, enter. And I end up getting X bar equals negative 0.031 and SD equals 0.0164. All right, at which point I can plug those into my equation. So negative 0.0132 or 031 minus our difference of 0 over the 0.0164 divided by the square root of 2 equals the probability, and let's figure out where we got that from. To do that, all we did was go stat, put that over here, stat, arrow over to the word test, and we're looking at number 2, which is the t-test. We have data, so we want data highlighted, mean is 0, list is L3, frequency is 1. Now make sure on this that because our alternative hypothesis was less than, we have less than selected. Press calculate, and we get negative 2.776 equals 0.009. So our p-value is 0.009. They didn't give us an alpha, so we're going to choose 0.05. So we reject the null, all right? Because anytime our p-value is less than that, and by the way, it really helps to make these the same length, and 9 is definitely less than 50. Our p-value is 0.009. We reject the null. There is sufficient evidence that alpha equal 0.05 to suggest the true population mean difference in reaction time, dominant minus non-dominant, you must tell me which way you went, is less than 0. Our conclusion is that Professor McNeil is right. The dominant hand is faster. We have evidence to indicate that it would happen. Why? Tenths, hundredths, thousand. So if I were drawing the graph, which I should have already done, mean difference of 0, we ended up with a negative 0.0131. Shaded this way, this is our X bar. This is our population mean claim. There is a 9 in 1,000 chance of getting a test statistic as extreme as negative 0.0131 or more extreme if this was true. In other words, if this was true, this would only happen 9 out of 1,000 times, and we just don't think we're that unlucky. We're saying, hey, we're wrong 5 out of 100, but we won't be wrong 9 out of 1,000. So we're rejecting this. We're rejecting this claim and saying, you know what, the dominant hand is faster. All right. So that concludes this one. The next video will be scenario 2, confidence interval.